Hello everyone. What I'd like to do in this video is let's start talking about how we can combine functions. Given any two functions, heck even given 3 functions, 4 functions, 10 functions, we can combine those functions to make a new function in a few different ways. One main way we can do this is by adding functions. We can also subtract them, we can multiply, or we can divide functions. We can also compose function, plugging one function into another function. We'll talk more about that in the next video. Specifically here what we want to do is we want to know how to add, subtract, multiply, and divide functions. But the big question is once I'm given two functions and I combine them in a certain way to create a new function, what is the domain of our new function? And that's what we want to look at. So before I go on, I'd just like to talk a little bit about some set notation. So let's talk about some set notation. Okay. So let's say we want to talk about a set. Now oftentimes sets are denoted with capital letters. So let's say we have a set A, and for an example, let's say this set, I don't know, maybe we're at a casino and we're rolling the dice. So maybe what's in this set is, maybe if you want to bet on A, how could you win? And this maybe you're betting on rolling an even die. So you would win if you rolled a 2, a 4, or a 6. Let's say there's another bet, we'll call this the set B, and maybe you would win if you rolled the first 3 numbers on the dice, or on the die. So if you rolled a 1, a 2, or a 3, you would win. Okay, so let's think about how we can combine these sets. We can do that by using what's called a Venn diagram. Okay, so I'll draw 2 of these. Okay, let's have this be set A and this be set B. Let's have this be set A and this be set B. Okay, so what we're going to put here in the overlap of the two sets is what's in common between them. So maybe you would be wanting to know, how could I win both these bets at the same time? Well, you could win both these sets at the same time if you rolled a 2. So I'll put a 2 here. Okay, maybe you would only win, you would only win bet A if you rolled, let's see, what, a 4 and a 6. And you'd only win bet B if you rolled a 1 and a 3. But if you rolled a 2, you would win both bets. So here's a 4 and a 6. Here is a 2 and a 1 and a 3. So I guess if I want to draw a box here, how would you lose? How would you lose? How would you lose both of these bets at the same time? Well, that's maybe if you roll a 5. That's maybe if you rolled a 5. You would lose both of these bets. Okay? So maybe we're curious about how could I win them both at the same time? So we would want to make sure we rolled a 2. Now we call what's the overlap of these sets, we call it the intersection. So this is the intersection of A and B. So we would denote this as A, and a math symbol we use is an upside down U. So here we have an upside down U. So this means A intersect B. That's just me wanting to know what's in both of these sets. So if I were to write this is a new set, what's in that set? Well, what's in that set would just be the number 2. Now, maybe you'd want to know, well, how could I win at least one of the bets? Well, I'd want to know what's in A and what's in B, or A or B. So in this case, we would call this the union of A and B. I'd win if I'm in A or I'm in B. The union of A and B. So we would write this as A, and we use a regular U, A, U, B. This means union. What's in this set? Well, how could I win? I'd win at least one of the bets if I rolled a 1, a 2, a 3, a 4, or a 6. Okay, notice I didn't record 2 twice. Okay. So for whatever reason, I like to think of at least union, the word union. I don't know, that reminds me of marriage reminds me of marriage. So in that case, what would be the union? Well, with your significant other, well, you would get everything that if it's me and my wife, we get everything that I have, we get everything that she has, and we get everything together. So I don't know. I get, I don't know. She gets all my Seahawks posters, and what do I get? I get all her arts and crafts stuff. But there's stuff that we also got together. We bought a couch and a TV together. So the union is everything. Everything she has, everything I have, everything we have together. What would be the intersection would be just everything we got together. So that would be like the couch and the TV. That's how I like to think of it. Okay, we've actually already seen this notation here before, or maybe we haven't seen it, but I've talked about it. Remember when we were doing those domain problems in the last video, and I was trying to figure out what's the domain of this function? Well, we drew on a number line, the arrows kind of denoted the sets, and we wanted to find what was in common between those sets. That would be the intersection. If I want to know what was the union, I want to know what's in both sets. Okay. So let's go ahead and do, let's write up some definitions. It's going to be a little bit formal here for a second, and then we're going to be doing a bunch of examples. Okay, so let's say I have a function f of x. So we have a function f of x, and we have a function g of x. So these are our functions, and I'll denote their domains, what's allowed to be plugged into these functions. I'll call the domain of f d sub f. This is the domain of f. It's a set. And this will be the domain of g. This is all the numbers that I'm allowed to plug into g. So now let's say that we want to create new functions. So let's say I want to create a new function. Maybe I want to add these functions together. So I'm going to give this new function a name, and I'm going to put that in parentheses. Okay, what's a good name for me saying I'm adding these two functions together? A great name for this function is just f plus g. Now this is just a name. I'm giving the name of this function f plus g. You could call it h if you wanted to, but a good name for this to tell the reader what we're doing is we're going to call this function f plus g. So f plus g of x. Okay, what does this mean? What this means is I'm taking the outputs of f and I'm adding them to the outputs of g. Okay. So now what would be the domain when I add these two functions together? Well, the domain of our resulting function, the domain of f plus g, well, has to be everything that works for f, but it also has to work with g. So it has to be the intersection of these two sets. Here's a quick example. Let's say that f of x is equal to the square root of x plus 3. And let's say that g of x is equal to the square root of x plus 5, for example. For this function, what I need x plus 3 to be greater than or equal to 0, so x has to be greater than equal to negative 3. Over here, I would need x plus 5 to be greater than equal to 0. So if I subtract 5 from both sides, x has to be greater than or equal to negative 5. So here, the domain of f is going to be all x such that x is greater than or equal to negative 3. And here, the domain of g is got to be all x such that x is greater than or equal to negative 5. Now, I want to know what the domain of f plus g is, so I need to find the values of x that work for both of these. So I need to find the intersection of these two sets. So if I were to graph this, okay, here I'm have like a negative 3, so this would kind of be like my A bubble, except I'm not writing it as a bubble, I'm writing it as a line. So all x such that x is bigger than or equal to negative 3. But I also need to find, here's negative 5, I need to also have all values of x that are bigger than or equal to negative 5. So what's going to work for both of these, if I'm going to add these functions together, if I added them together, the function f plus g of x would be equal to the square root of x plus 3 plus the square root of x plus 5. So this would be f plus g of x. Well, I need to find values of x that work for both of these. I need to find the intersection of these two domains, and that's going to be the overlap. That's going to be the overlap here. So the domain of f plus g, that's going to be equal to all x such that, well, What's in common between these two sets? Just all x that's greater than or equal to -3. This is the intersection of those two sets. Okay. We'll be doing a lot more examples. Okay. So we could also subtract functions. So what does it mean that I'm creating a new function that subtracts them? This is just the name of the function. What does it mean? It means I'm taking the outputs of f and I'm subtracting them from the outputs of g. And similarly, the domain of f minus g, well, it has to work for both of these, so it has to be the intersection of those two domains. Similarly, we could multiply functions together. Okay, take notice that I'm putting a filled in dot right here. For compositions, we'll do an open dot. We'll talk about that more later. But just be careful when I'm doing multiplication. It's a closed dot. What does it mean to multiply two functions together? That means I'm taking the outputs of f and I'm multiplying them by the outputs of g. And similarly, the domain of this has to work for both of them. What's the domain of f times g? Well, it has to be everything in the domain of f and everything in the domain of g, which just means the intersection of those two sets. Now, the last case, what if I could divide two functions? Now, what this means is I'm taking the outputs of f and I'm dividing them by the outputs of g. Now, we need to be a little bit careful with this one when I want to find the domain. The domain of f over g, the domain of f over g, is going to be everything, well, the domain of f and g, let's write this maybe in a different way. It's going to be, I'm going to write it as a set, it's going to be all x such that, well, it has to work for both of them, so all x, this symbol here, this kind of funky looking E means is a member of. Let's scoot this over a little bit. So the domain of f divided by g, we'll write it as a set. It's all x values such that, well, it has to work for both of them. So all x that are a member of the intersection, so it has to work for both of them. But I need an extra condition here. It's everything in there, but also I need to make sure to exclude values. I need to exclude values that make g of x 0. And all values of x such that g of x is non-zero. So I can, everything that's in both the sets, but I also have to exclude values that make the denominator 0 because I cannot divide by 0. This seems very fancy and very formal, but in practice, it's not too bad. A lot of times when you're first looking at math, I don't know, this seems kind of crazy. Look at all these symbols. But if you break it down, it's really not too bad, specifically when we start doing examples. So let's do it. Okay, so for our first example, we'll start kind of simple. Let's say we have the function, let's say f of x is x squared plus 6x plus 8. And let's say that g of x is equal to x squared plus 4x. Okay. Now let's combine these in a couple different ways. I guess before we start combining them, let's ask what the domain of these functions are. Okay, what is the domain of f? So if you look at these functions, these are polynomials, and we learned how to graph those. And if you think about the graph of those functions, well, every single value you plug into those functions is going to give you a meaningful output. So the domain of these should be all real numbers. Now, if this is confusing you, just run through our checklist of domain restrictions. We're going to ask ourselves the question, am I ever going to divide by 0? I don't see any denominators, I don't see any variables in a denominator. I'm never going to be worried about dividing by 0. Okay, second thing on our list, are we ever going to be taking the even root of a negative number? Notice I don't have any square roots, I don't have any fourth roots, I don't have any 10th roots, I don't have any even roots, so I'm never going to be worried about taking the even root of a negative number. So I'm not concerned about any of those. I'm never going to break condition 1 or condition 2, so the domain for these functions will be all real numbers. So I can write this in a couple different ways. The domain of f is going to be all x such that, well, x is a member of the real numbers. Another way to write this is you could say that x is in the set negative infinity to infinity. These mean the same thing. And again, this fancy E, it's very common. It just means x lives in this set. That's what it means. Or x is a member of this set. Okay, and similarly, the domain of G is going to be all x such that x is in R, or all real numbers. Similarly, we could say x is in negative infinity to infinity. Okay, so let's start by creating a new function, f minus g of x. So what this means is I want to take my function f, and I want to subtract it from my function g. I'm sorry, f of x. I want to take the outputs of f, and I want to subtract them from the outputs of g. Okay, so how could we do this? Well, let's see. F is going to be x squared plus 6x plus 8. And I'm going to be subtracting x squared plus 4x. Now, a very common mistake I see students make with these is forgetting to put parentheses around the second function. Remember, when I'm subtracting a sum, I have to subtract all the pieces. You need to distribute that minus sign. It's like, for example, if you took 10 and you're taking away 7, you should be left with 3. But you could also, 7 is the same thing as 3 plus 4. So if you're taking 10 and you're subtracting 7, well, you need to take 10, you need to take 3 away, and also take 4 away. So you're left with 3. Okay, hopefully that made sense. So that's why we need to distribute minus signs. So what we'll have here is we'll have x squared plus 6x plus 8 minus x squared minus 4x. So now we can go ahead and clean this up. Notice that these x squareds cancel out. X squared take away x squared, I have 0 x squareds left. I have 6x take away 4x, I'm left with 2 x's left. Combined those together, and then plus an 8. So what we have here is we have our new function, f minus g of x is equal to 2x plus 8. Okay, so what I would like to say here is now, what is the domain of this function? What is the domain of f minus g? Well, it has to be the intersection of these two sets. So while this is going to be kind of silly, let's kind of just draw it here really quick. So here is 0. Okay, let's do the domain of f in green, and let's do the domain of g in blue. Okay, so what can I plug into f? I can plug in any real numbers. What can I plug into g? Any real numbers. What can I plug into f minus g? What works for both of those functions? That's going to be the intersection, which is, again, all real numbers. So the domain of f minus g is going to be all x, such that x is a real number. Or you could just write from negative infinity to infinity. Both mean the same thing. Before I go on and do a different example, why do we care about subtracting functions? Well, if you're doing a job and you have to do a lot of inputs and outputs, or maybe if you're a computer programmer and you need to take the outputs of this function and subtract them from this function, it's a lot more work for me to first evaluate this function at a value, then evaluate this function at a value, and then subtract them. That's like 3 operations. This is actually more than that because when I plug in a number, I'm squaring it and multiplying and adding. But plug this number in, get an output. Plug this number in, get an output. Subtract them. Rather than me just plugging in one input and getting out one output. I mean, notice, this would be such a pain in the butt if you had to do it this way. Let's erase a little bit of this here. Why do we care about doing something like this? Well, maybe you wanted to know maybe we wanted to do f minus g of, I don't know, how about of negative 2? Now, not a very nice way to do this would be calculating it like this. F of negative 2 minus g of negative 2. So I'd have to evaluate each of these functions at negative 2. So f of negative 2, what's that going to be? That's negative 2 squared plus 6 times negative 2 plus 8. What are we going to get here? That's what? That's 4 minus 12 plus 8. 8. Oh, so what is that? That's 0? Okay, cool. So this is output here is 0. So maybe this wasn't a great number to plug in. I get an output of 0, but still, now I'm going to evaluate g at -2. G of -2, what's that going to be? That's going to be -2 squared plus 4 times -2. So what do we get there? We get a 4 plus a -8. Looks like we get out what? A -4. So it would be 0 minus a -4, you're going to get an output of 0 plus 4, you're going to get an output of 4. Look how much work that was. Then me just doing this, or us just doing this. What's f minus g? What's f minus g of -2? Well, just use this formula, or this machine that we built. That's 2 times -2 plus 8. I get out -4 plus 8. I get out a +4. Look how much easier that was than me having to do 2 evaluations and then subtract the results, when I can just build one machine that does it all for us. So that's why we like combining functions. Okay, so let's do another example. So we did f minus g. Okay, let's keep this up. Let's also do, be a little bit careful, let's do the division of these. Okay, so this was the domain of f. Let's say we want to compute f divided by g of x. So that's going to be, what does this mean? This means we're taking f of x and we're dividing it by g of x. So that's going to be x squared plus 6x plus 8 all over x squared plus 4x. So I've divided these two functions. Okay, now we can go ahead and simplify this if we'd like. So let's see here. In the numerator, let's see, how can we factor that? That'll be, what, I think I need a 4 and a 2, so this will be x plus 4 and x plus 2. All over, I can factor out an x, and I can get an x plus 4. Okay, so what we need to do in this case is, I guess we can simplify this. We can simplify this by canceling out the x plus 4s. So I'm left with x plus 2 all over x. So here we have f over g of x, or f divided by g of x is equal to x plus 2 over x. This is something so much simpler to work with than evaluating this polynomial, and doing the division. It's so much easier to work with this. Okay, but now what's the domain? So we need to be careful. So the domain of f over g, we need to be careful to not just look at the simplified version. Well, it's everything that's in the domain of f and everything that's in the domain of g, so that's all real numbers, but remember I need to exclude the values that make the denominator 0. If I look over here, we're staring over here, notice that x cannot be 0. That would be, that's the value of x that makes g of x 0. And also, x cannot be equal to -4. Even though they canceled out, that would be making the denominator 0. Notice if I plugged in -4, I'd get 0 divided by 0, which is what we call an indeterminate form. You learn so much about indeterminate forms when you get to calculus. It's a very important idea to keep track of. Also, this is saying that for this rational function, there's a hole in the graph at -4. The function is not defined there. So the domain of f divided by g, it's going to be all x such that, well, it can be any real number, but x cannot be 0 and x cannot be equal to -4. So that would be, this is the resulting function when I divide them, and this is its domain. Okay. So be careful when you're dividing functions and you're simplifying. You need to make sure to look at the version before you simplify and define the values of x that you can't plug in, and then simplify and report your final result. Okay, let's do another example. Okay. So let's say, for example, that we have the function, how about f of x is equal to, how about 1 over x minus 2, and let's say g of x is equal to the square root of x plus 1. What I would like you to do is I want you to find the domain. Let's have you compute, how about f plus g of x, and let's also have you compute, how about f times g of x, and find their domains. Go ahead and give this a shot. Okay, let's do it. For f plus g of x, there really isn't too much to do here. So I'll say that this is going to be equal to, what am I doing? I'm just taking f of x and I'm adding it to g of x. So I'm going to get a 1 over x minus 2 plus, looks like the square root of x plus 1. You could go ahead and maybe if you want to find a common denominator, you could add these together. But for this specific example, I think it's fine for us to leave it like this. So this is the same thing as f plus g of x. Really not much to this one. So what are we going to do here? Let's see this now. Let's just try to find its domain. Okay, well, what's the domain of f? The domain of f, I'm only worried about dividing by 0, so all x such that x can't be equal to 2. Okay, over here, I need the domain of g of x. Well, what do we need? We need x plus 1 to be greater than or equal to 0, so x has to be greater than or equal to -1. So this will be all x such that x is greater than or equal to -1. Okay, so let's think about what the domain of this function is. It's great for us to draw this. Okay, so for f, I just have all values of x such that x can't be equal to -2. Let's go ahead and, how about we draw this one in green? So what does this look like? Well, if we're over here at, let's say here's 2, I can plug in any number. I can plug in any number besides 2. What does this set look like? How about in blue? Well, this is all x that's greater than -1. Greater than or equal to -1. So like this. So if I want to find the domain of the result, I need to find the intersection of those two sets. So that'll be this set here. So I can plug in any value bigger than -1, but I also have to note that I have to exclude 2. So the domain, I'll draw it in black here, will be this set here. So the domain of f plus g of x, the domain of f plus g of x is going to be equal to, let's see, this will be all x such that x has to be greater than or equal to -1, and x cannot be equal to 2. Okay, there's a couple other ways we could write this. We could say that, how about that x could be between -1 and 2, or we could say that it's between 2, x is between, or how about x is bigger than 2. X is bigger than 2. So this would be the domain of the set. Or you could write this as, this could be from -1 to 2, soft bracket, intersection, not intersections would be the union, and from 2 to infinity. Because what I want is, I want this set, I kind of have like two pieces here. I want this set, and I also want to include this set. So I want the union of these two pieces. I want these two pieces together, and that's why I'm putting the union symbol here. This is how we'd write that domain in 2 different ways, or it looks like 3 different ways. Okay. If we were to multiply them together, so erase this. If we were to multiply them together, f times g of x, so f times g of x, well, this is going to be f of x times g of x. Okay, so f of x is 1 over x minus 2, and g of x is equal to the square root of x plus 1. So if we multiply these together, we're going to get the square root of x plus 1 all over x minus 2. So this is f times g of x. And the domain is going to be the same thing. It's going to be the intersection of these two sets, which is what we have here in black. So the domain will be exactly the same as when we added them. So here the domain of f times g of x is going to be all x such that x is greater than or equal to -1 and x cannot be equal to 2. Sorry about that slanted writing. Okay, let's do another example. Let's say we have f of x is equal to the square root of x plus 2, and we have that g of x is equal to the square root of 3 minus x. And let's compute f minus g of x and state its domain. And let's also compute, how about f divided by g of x and state its domain. Okay, go ahead and pause the video and give this one a shot. Okay, for the computation, there's really not too much to do here. For this one, this is just going to be, I'm taking f, so the square root of x plus 2, and I'm just subtracting it from the square root of 3 minus x. There's no combining we can do here with these square roots. I can't distribute this minus sign inside the square root. This is as far as we can go with this function. There's not really too much more to it. Okay, so this is f minus g of x. Now let's think about its domain. Let's draw its domain. Here's the domain of, how we do the domain of f in blue and the domain of g in green. Okay, so what needs to be true for f? Well, what we need x plus 2 to be greater than or equal to 0. So we need x to be greater than or equal to -2. And for g, we need 3 minus x to be greater than or equal to 0. So we need negative x to be greater than or equal to -3. Multiply both sides by a negative, that'll flip the inequality sign, so x will be less than or equal to 3. Okay, let's sketch this. Okay, so for x, so we're here at -2. I need everything greater than or equal to -2. For g, I need all values of x less than or equal to 3. So if I want to know the domain of the combination of these, or the domain of the subtraction, that'll be everything that's in common, or the intersection. So we have here that the domain of f minus g of x, that's going to be all x such that, well, if you think about x here, x is between -2 and 3. So -2 is to the left of x, and x is to the left of 3. This just reads that x lives between -2 and 3. Equivalently, you could write this as -2 to 3. Both have hard brackets. So this is the answer to the problem. So here I just decided to write the domain in 2 different ways. You could also write it without the curly brackets here if you'd like. And that would be what we call inequality notation. Okay, now this is going to be a little bit different when we do f divided by g. This will be the square root of x plus 2 all over the square root of 3 minus x. Okay, there's really nothing we can do here. We're just going to leave it exactly how it's written. So let's go ahead and think about its domain. Now the domain is going to be the same thing, but I have to remember there's an extra condition here. I still need x plus 2 to be greater than or equal to 0. So I still need x to be greater than or equal to -2. I still need 3 minus x to be greater than or equal to 0. So I need x to be less than or equal to 3. But I have to exclude values that make the denominator 0, or that make g 0. So I also have to note that x cannot be equal to 3. If you were to plug in 3, the square root of 3 minus 3, the square root of 0 is 0. So I have to exclude 3. So I have these 3 conditions I have to put all together. So now if I want to slap on that just x can't be equal to 3 here, what I'm going to do is I'm just going to put now an open bubble right here. Maybe I'll do that in black. So now we have that the domain of f divided by g, well, that's going to be all x such that, well, x can be between -2 and 3. It can be -2, but it can't be 3. So this is f divided by g, and this is the domain of f divided by g. Okay, let's do one last example. Okay, let's say that we have the function, let's say we have f of x is equal to x minus 1 all over x plus 5. And let's say we have that g of x is equal to, let's say x plus 6 all over x plus 5. What I would like you to compute is I'd like you to compute f minus g of x and find its domain, and also compute, how about, let's do g divided by f of x. So go ahead and pause the video and give this a shot. Okay, let's do it. The first thing I'm going to note here before I do anything is let's talk about the domain of these functions. I hope you believe that the domain of f, the only thing I'm worried about here is possibly dividing by 0. The domain of f is all x such that, well, x cannot be equal to -5. Over here, the domain of g, this is going to be all x such that also x cannot be equal to -5. Okay, let's first start by subtracting them. So I need to take x minus 1 all over x plus 5, and I need to subtract an x plus 6 all over x plus 5. What's nice about this example is I have a common denominator of x plus 5, so I can just subtract the numerators. If we had a different denominator, you would need to find a common denominator. Okay, so what I'd have here is I'd have an x minus 1. Now don't forget your parentheses. I do have to do a minus x plus 6 when I'm subtracting the numerators, all over our common denominator of x plus 5. So we can distribute in this minus sign. So what are we going to get? We're going to get x minus 1 minus x minus 6 all over an x plus 5. So, awesome. The x's cancel. So I'll be left with -1 minus 6. I'm going to get a -7 all over x plus 5. So this is going to be f minus g of x. Okay. Let's talk about its domain. The domain of f minus g, okay? Well, it has to be everything that's in the domain of f and everything that's in the domain of g. It has to be the intersection of both of these. Well, since they're the same domain, the domain of f minus g is still just going to be all x such that x cannot be equal to -5. Okay. So here's the domain. Let's do g divided by f. Okay, what are we going to get here? I'm going to take our function g, which is x plus 6, all over x plus 5, and I'm dividing that by x minus 1 all over x plus 5. So let's go ahead and simplify this. So what this is saying is how this reads is I'm taking x plus 6 all over x plus 5, and I'm dividing that by x minus 1 all over x plus 5. Remember how we divide fractions as we flip and multiply. This is x plus 6 all over x plus 5 times an x plus 5 all over an x minus 1. So if we multiply these together, I have an x plus 5 over an x plus 5. I got that secret 1 that's lurking there in the bushes. We can cancel out that x plus 5, and we'll just end up getting out. What, an x plus 6 all over x minus 1. So this is the function g over f of x. Okay, so this is g divided by f. Now what's its domain? Well, the domain of f let's see here. Well, the domain of f, g over f. The domain of g over f. Well, that's everything that's in the intersection of both of these. So notice that x cannot be equal to -5. X cannot be equal to -5, all x, such that x cannot be equal to -5. And also, I need to exclude values that make the denominator 0. I need to exclude the values at which f is 0. Well, when is f 0? Where are the x-intercepts of f? That's when the numerator is 0. Notice here that f of x is equal to 0 when x equals 1. So I need to also exclude the value x equals x. I can't plug in 1. X cannot be 1. So this would be the domain of g divided by f. Okay. I know this kind of looks like when you're looking at this formula, it seems like you can plug in 5. But remember what we're doing is we're taking the outputs of this function, and we're taking the outputs, I'm doing g first. I'm taking the outputs of this function and dividing it by the outputs of this function. Well, this function's not defined at 5. So if I try to plug in -5, I'm not going to get a meaningful output. So how can I divide them? So even it looks like things canceled here, I have to look back at my original functions to think about what the domain of the combination is. Okay, that's all I have for this video. I hope you enjoyed it. And the next one, what we're going to start doing is we're going to start talking about compositions of functions. How do I, basically what a composition is plugging one function into another function. That's really one of my favorite ways to combine functions. A very important idea in calculus. So let's go ahead and end this video here, and we'll see you in the next one. Take care.